Welcome back to The Explainer. Have you ever really thought about what's happening behind your eyes as you watch this? Today, we are diving deep into the human eye, how it works, and how it translates simple light into the beautiful, colorful world we see all around us. So let's start with this. The camera you have in your head is, without a doubt, a piece of biological engineering that's way more sophisticated than anything you could buy in a store. It's capturing images, constantly adjusting to light, and streaming all that data to your brain in real time. It's just incredible. And get this, all of that power, all that amazing machinery is packed into a tiny sphere, the eyeball, that's only about 2.3 centimeters across. That's smaller than a ping pong ball. Okay, so here's our game plan. First, we'll look at the eye as a living camera. Then we'll follow a ray of light on its journey. We'll get into the magic of focusing, then touch on how we fix vision when it goes wrong. And finally, we'll see how we decode light and color. All right, let's start our tour. The very first stop for any light ray entering your eye is this transparent front window, the part that's literally making first contact with the outside world. And that window is called the cornea. Now, it's not just a protective shield. No way. The cornea is a powerhouse. It does about 80% of the initial bending or refracting of light. It's doing most of the heavy lifting for focusing before the light even gets to the lens. So once the light zips past the cornea, its journey continues deeper inside, and that's where it meets the gatekeepers. These two work together in a really cool way. The iris, that's the colored part of your eye, it acts just like the shutter on a camera. It's a muscle that physically changes the size of the pupil, which isn't really a thing at all, it's just a hole. This is why your pupils shrink in bright sunlight and get huge in the dark. It's the iris controlling exactly how much light gets in. Okay, after slipping through the pupil, that light hits the crystalline lens. You can think of this as the fine-tuning focus ring on our camera. It's this amazing, flexible little lens that makes tiny adjustments to create a perfectly sharp image. And here's a wild fact. That image it creates is actually upside down. So how in the world does this flexible lens change its focus so fast? Well, this is where the real magic happens, and it's all thanks to some tiny but super powerful muscles. Right, so to look at something up close, like the phone in your hand, your ciliary muscles actually contract. They squeeze in, which makes the lens bulge out and get thicker. A thicker, more curved lens has more focusing power, which is exactly what you need for things right in front of you. And what about looking at something far away, like a plane in the sky? You guessed it, the exact opposite. Those same muscles relax, which allows the lens to stretch and become thinner. This reduces its focusing power, making it perfect for seeing things in the distance. Now that focused, upside-down image has to land somewhere, right? It lands on the retina. This is basically the movie screen at the very back of your eye. It's a light-sensitive layer that's just packed with millions of special cells that are ready to turn that light into real information. And on this screen, you've got two main types of cells. You've got rods, which are the superstars of low-light situations. They give us our night vision. And then you have cones, which handle bright light and, crucially, give us all the color we see. Just remember, C for cones, C for color. The moment light hits either of these, boom, they fire off an electrical signal straight to the brain. But you know, this system is so incredibly intricate that it doesn't always work perfectly. If that focus point is just a little bit off, the image on our retina gets blurry. So let's talk about two of the most common ways this can happen. First up is myopia, but you probably know it as nearsightedness. This is when you can read a book or your phone perfectly, but the menu board across the room, it's just a fuzzy mess. So what's actually going wrong here? Well, in a nutshell, the light is being focused too early. It's creating a sharp image before it even gets to the screen at the back of the eye. Yep, the light focuses in front of the retina, not on it. And that usually happens for one of two reasons. Either the eyeball itself is a little too long from front to back, or the cornea and lens are just a bit too powerful and they're bending the light too much. The fix? We use a concave lens and glasses to spread the light out a bit, pushing that focal point back so it lands perfectly on the retina. Now, on the flip side, you've got hypermetropia, or farsightedness, and this is the exact opposite issue. That sign down the street might be crystal clear, but trying to read the text on a medicine bottle becomes a real challenge.
And what's the problem here? Well, it's the mirror image of myopia. This time, the light just isn't being bent enough by the time it reaches the back of the eye.
In this case, the light is trying to focus at a point behind the retina. This happens because the eyeball might be a little too short, or the lens just isn't strong enough to bend the light sharply. So, the solution is a convex lens, one that helps converge the light a little sooner, pulling that focus point forward so it lands right where it's supposed to. And when you look at them side by side like this, it's just so clear, isn't it? They are perfect opposites. The problem, where the image forms, the cause, and even the kind of lens you need to fix it, it's all a mirror image. All right, for our last section, let's put it all together. We've talked about the hardware of the eye. Now let's get to the really fun part. How does it perceive the amazing, colorful world we live in? And it all starts with unlocking the secrets that are hidden inside plain, old white light. Think about a rainbow for a second. The magic of color is happening inside every single one of those raindrops. As sunlight enters a drop, it bends and splits apart into a full spectrum of colors. Then, those colors bounce off the inside back wall of the raindrop. And finally, they bend one more time as they exit, sending that beautiful arc of color straight towards your eye. So when you think about it, our eyes and our brain are working together constantly to build this incredibly vibrant world, all from simple wavelengths of light. It's an amazing biological feat. And it kind of leaves you with one last big thought. If this is what we see, what other realities might be out there, hiding in the parts of the light spectrum that our eyes can't even perceive?